talk about how we can use physics-informed neural networks to model proprioception. So I'm actually in the field of computational neuroscience, and one of the things that we do there is build models to understand the brain, and especially how the brain creates behavior. So what does that look like? Well, one behavior can be movement. And this is quite remarkable, considering especially that we've been trying to build robots to do anything kind of similar to this, and we cannot achieve the same performance. And it's also quite remarkable if you actually look inside the brain to try to understand what are the biological constraints to actually achieve this movement. And it's a quite difficult problem. You have the brain has to use a lot of sensory information from all kinds of sensors and integrate that to make decisions on sending motor commands. Those are instructions to all the muscles, every muscle in your body, on when to contract at the perfect timing in order to produce this coordinated movement. So because I only have 5 minutes, I'm going to talk to you about how we can model one specific part, which is proprioception. Proprioception is the sense of where your body is and what it's doing that you can have even if you close your eyes. It lets you achieve all these movements, no? And it comes from all these sensors across your body, tendons, muscles. And one particular very important one are muscle spindles. So muscle spindles are in muscles, and almost all the muscles in your body are going to have hundreds or thousands of muscle spindles. So when you think of a muscle, you think of these fibers that contract to create movement, no? But actually, between these fibers, you can find these capsules, which are the muscle spindles. They're also composed of fibers, but they don't create the movement. What they do is send back information to the rest of the nervous system on what the muscle is doing. And to do that, they use sensory neurons. That's how all information is carried around the brain, through neurons. So they're transforming a mechanical signal, which is the lengthening or the shortening, into a firing rate. So you can think very simply like this is a way of transforming muscle stretch into spindle firing rate. No? So if I lengthen a muscle, the firing rate increases, or if I shorten, the firing rate decreases. No? But this is a very hard problem actually to model. We have recordings perhaps of the spindle firing rate, but actually these can vary so much depending on which spindle you're measuring and across animals and even within the same individual. Furthermore, even though we know a bit about the physiology here, we don't know enough. So what we do in computational neuroscience, we try to model this. And we can take many approaches. So on this side of the spectrum, we use a lot of machine learning, data-driven, statistical-driven models. And they have been very, very successful in modeling vision with CNNs, RNNs to model some form of motor behavior. But on the other side, we also love using very physical and mechanistic models because those are the ones that really tell us how the brain is doing things. How are these systems really working? So on this side, we need usually small data to model this, but we need a lot of knowledge of the system. On this side, we need a lot of data, but perhaps it gives you a bit less knowledge about actually how the system is functioning. On this spectrum, you can have many models, and you've heard many times today already, talked about physics-informed neural network. And the surprising thing, not really being used in computational neuroscience despite how popular they are in other fields. So in our case, how do we use a physics-informed neural network? So we have some training data, in this case from a lot of recordings, not so much data, but enough. And then we have some knowledge a bit of the system. And in this case, even though we're not certain exactly what the right differential equation is, we can take from other knowledge of like what muscle fibers can do. So what we're going to use is knowledge on the differential equation on the tension inside these fibers. So this is a bit what our model looks like. So our neural network is outputting the tensions, and they're transformed with this module into a firing rate. And we can use the training data to train to the data loss, and then we can use the knowledge of our differential equation to train with the OD loss. We have a combined loss. And then we use data from different situations. So on the left, we have recordings from cats doing passive data, passive movements, and humans on the right, active movements. And already you can see, even though the muscle length is quite different, but also the responses are quite nonlinear, especially in this case, in these active movements. So we were able to achieve quite good prediction. But not only that, now we have a model that can predict the behavior of this complex system, but also it can give us a glimpse of what's happening inside, because we can get actually recordings or predictions or what the tensions inside these muscle fibers are doing, even though these are not measurable quantities. So just as a quick summary, we build with physics-informed neural networks, you can build a model that's quite data efficient, but can also capture some of the intricacies of the mechanisms of this biology. And even more importantly, we can integrate these then into bigger models of sensory motor control. I want to thank the lab and our collaborators.
Thank you very much, Adriana.